Hello, my name is Gonzalo Abad, and in this video tutorial we are going to see asymmetrical voltage dips analysis in a wind turbine based on doubly fed induction generator. More specifically, we are going to see the grid side converter control when we have asymmetrical voltage dips at the grid side. Most of the information related to this topic can be found on this book, Power Electronics and Electric Drives for Traction Applications, which has been edited by Wiley. And the information related to this topic can be found in chapter 4 of this book. Okay, so if we go to the program file, to the Simulink program file where we left in video tutorial 7, I think it was, we will continue from this Simulink control block diagram. If you remember, we perform at the grid side asymmetrical voltage dip with this positive sequence and this negative sequence, and we perform it at second 3. Okay, so here we have a voltage dip which is asymmetric, which is unbalanced, and what we did in video tutorial 7 is, by means of the rotor side control, deal with this type of voltage dip which is asymmetric. And now in this video tutorial we are going to deal, or we are going to implement the required control strategy at the grid side converter in order to deal with this asymmetrical voltage dip, which is also seen by this grid side converter. Okay, so if we go, as I said before, to chapter 4 of this book, Control of Grid Connected Converters, and if we go to page 198, if I'm not wrong, here we have the control block diagram that we need to implement at the grid side converter. Since we have asymmetrical voltage dip here, since we have unbalanced voltages at the grid side, we will need to add to the positive sequence current loops, negative sequence current control, in order to tackle, or in order to deal with this asymmetry at the grid side. This is something very similar as what we did at the rotor side converter. This is something equivalent. If we go to page 200 of this book, if I'm not wrong, sorry. If we go to page 200, here we have the current sequence decomposition block diagram that we need to implement, more specifically, well, yes, for the grid side currents. Here we have ABC currents that they can be unbalanced or not. First of all, we need to use the Clark transformation in order to transform from 3 phases to 2 phases. Here the frequencies are 50 Hz, and then with the rotational transformations we can derive the negative and positive sequences of these grid side currents. Bear in mind, take into account that we need to use a filter for each D and Q component of each sequence, negatives and positives, in order to basically remove the coupling sequences one of each other. As this is 50 Hz, the coupling sequences, the oscillatory terms, will be 100 Hz, double frequency of this. And the positive and negative sequence the actual ones are DC at a steady state. So we need to remove these oscillations. Okay, so let's go now to the program, to the Simulink program, and let's go to the grid state converter control, and let's implement the control block diagram, which I have shown from book at page 198. So basically what we are going to add is just this negative sequence of current loops, as I said before. Then there are different ways of generating the positive and negative sequences, references for D and Q components. There are several ways to do it, and there are several objectives to fulfill. In this case, in order to be simple, we are going to just leave the negative sequence references to 0. And the positive sequences will be as we did or as we used in previous tutorials. The positive sequence D component, yes, D component will be responsible of controlling the DC bus voltage, and Q component of the positive sequence will be responsible of the reactive power. Okay, so let's go now to, for instance, first duplicate the current loops as always. Let's do it carefully. Let's copy this side, and this will be dedicated for the negative sequence. So here we need to add another term for the final addition. Let's put it rectangular because maybe it's more representative, and let's remove this element in order to be more symmetric, this box. Let's add the negative sequence secondly, and then add the feed forward term coming from the stator or from the grid voltage third. Let's do it in that way. For example, these are the positive and negative sequences. Okay, let's have a look as to the name, positive and negative, to the names that we gave to the rotor side converter control. So let's do the same again. Let's call to this positive. Sorry. This is positive, and this is also positive. Let's do the go-to a little bit bigger. Let's remove these lines because otherwise we have too many lines altogether. So let's use more go-to blocks. Okay, as I said before, we are going to left the references of the negative sequences to 0, so we need a constant for the D component of the negative sequence and for the Q component. Sorry about this. Okay, and therefore this is going to be negative. So let's add the negative term and let's connect it there, and let's add here another go-to for the positive, sorry, for the D component of the negative. 0, 0, positive, positive. Okay, this is just one part. Okay, so the cancellation of the coupling terms are in this way for the positive sequence, and you know that the negative sequence is always in the other way around with these signs. So this is positive and this is negative. Okay, so these are the loops. And now what we need is, yes, the PLL. Here, when we need to deal at the grid side converter, at the grid side with unbalanced voltages, what we need, as we did in previous tutorial at the rotor side control, we need a PLL. That we can take it from here, and then we will need this also, so I will copy all. Where we are, sorry, here we are. We need to come again to the grid side converter control. We go there and we add the PLL, which is able to deal with the positive and negative sequence at the voltages, at the grid voltages. So we don't need this anymore. This is, we need to take it out pi over 2, and the parameters of the PLL are going to be just the same. We have duplicated this PLL. We could use just one because the functionality and is just duplicating one block, two blocks, which are doing the same. We could use one block, but anyway, let's use two. It is not so important. Okay, so this is the angle theta for the positive sequence. Then we need, as we have said here, we need the current sequence decomposition. This is the grid synchronization by means of a PLL, by a simple PLL. This is what we did. We have taken the angle theta, and then we need to do the current sequence decomposition, which is in page 200, as I said before. And the thing that we need is the filter. If you remember in previous tutorial as well, this is very equivalent to what we are doing for the rotor side converter. We use one filter which is based on notch filters. Let's put them there, just in the middle, there and there. Let's copy and connect. So this is going to be the positive, so the component, let's add the P, and this is the positive Q component. And the notch filters, if you remember, are band stop filters, second order filter necessarily, with a damping ratio of 0.05. Obviously at 100 Hz, because the frequency that we want to remove is just that, 100 Hz, and this is the sample time. This is not recognizing the filter parameters because we didn't initialize the parameters, such as the switching frequency. So we initialize the parameter by means of the .m program, and now it should recognize it. So we can see the plot filter, the filter response. This is the step response, and this is the both diagrams for this filter. So we see here how it is rejecting the 100 Hz frequency, and here it is the oscillations that we are going to find at when we have a step response at these currents, at the input of these currents. By changing the filter parameters, such as the damping ratio, this term, we could do these oscillations and this response, this oscillations amplitude bigger and lower, but we will left it as it is because this is good enough. Okay, let's go back to the program, sorry. So this is the filter, and we basically need to do the same. Okay, so we need more space, and we need to copy the whole thing to here. Let's do it carefully. These are the DQ, the alpha beta components, and theta for the negative sequence should be negative in this case. So we need one gain like this, and we just need the opposite rotation sense of the space vectors. So therefore we need to put a -1 just in the angle. We will need some more space. Okay, let's do it there. And this is theta. Currents theta minus theta. Okay, so therefore the angle theta for the transformations must come from this one. Let's do it carefully again and connect it to there. Okay, there it is. Let's check it. This is voltage feed forward, so let's put it something farther away, and these are angle, theta angle and minus theta angle, and this is the feed forward voltage which comes there. Okay, what else? So now we need to use some frontus that probably can be taken from there, but before doing it, this is going to be, sorry, negative reference. This is going to be negative reference. And in this case, in this other block, we have something equivalent. So in this case, this is going to be positive, and this is going to be positive. Okay, so let's paste it there. Ah, no, sorry. We need a front two. We need a front two that can be taken from here, for instance. So this is going to be this current. So let's put it there. This is the positive one for the component, and the same, but in this case this is going to be Q component. So it's there, so everything is correct. And the same for the negative component, which is it's not there. Ah, sorry, I didn't change it here. So let's do it there first, and this is going to be Q but negative. So this should be now okay. And here Q component, EQG. Okay, it's the same, no? Yes. It's okay, it's everything, it's there. It seems that everything is correct. So the current loops are already created. Let's do it smaller. These are the positive and negative sequences, and this is the PLL. The PLL together with the sequence decomposition, which is the block diagram in here. And as I said before, we are not doing a very special reference generation, but in order to be simple, we are letting these references of the negative sequence to 0. Okay, so let's continue now adding the required go-to blocks or variables to the monitoring block. I don't know why it's not working. Yes, now it's working, the Zoom. So at this grid side converter control, we need to add the negative sequences that we have included in our control block diagram. Okay, so let's do a little bit bigger, and let's start from the positive sequence. This is going to be positive, it's there, so it's correct, and this is going to be the actual positive one. It's there, okay. And in the same window, in the same scope as we did the previous tutorial, we are going to also add, the negative sequences. So this will be negative. It's there, so it's great, and it is also there. This is for the currents of the positive sequence, and the voltage. And the voltage is, we need to do something equivalent, visualizing, being able to see both positive and negative voltage references. Okay, and let's do the same again for the negative. So this is going to be positive, negative, and this is going to be the actual negative, which is correct. Then we can copy and multiplex all these variables. And finally, we will need to say that this is Q. I did it wrong. This is the negative, so in order to be consistent with the order, this is positive. And this is going to be positive as well, but actual. Positive, 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 negative, 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 negative. D components and Q components. Okay, and the same for the voltage references. We add the multiplexer. It's there, and then we add another one, and we connect all together. So this is going to be positive, okay, and this is going to be negative. Okay, so everything should be there from the point of view of the visualization of the scopes. What else? Yes, once we have the voltage dip, that, as we have said before, but let's check again, is at second 3, and it will finish at second 4.2. As we did in the rotor side control, because the typical grid code requirements demands providing reactive currents through the stator of the DFIG and through the grid side converter of the DFIG. Let's have a look. When did we put it through the rotor? This is providing of reactive current at second 3.15. So let's do the same, or something equivalent with the grid side converter with a step, a very fast reference generation. And in this case, let's use, for instance, I don't know, minus 500 kilowatts. Negative, therefore capacitive. At second 3.15, which is 150 milliseconds later when the voltage dip occurs. Okay, so let's do it in that way. Depending on the grid codes of each country, probably depending on the grid code, we will require to provide these reactive currents through the grid side converter and through the rotor side converter by means to the stator, maybe faster, not in 150 milliseconds, but maybe even in some few dozens of milliseconds. But anyway, we don't want to go to a very demanding scenario or contest. So I think that everything is ready now. However, there is one last thing. As now here we are dealing with two pairs of current loops, 4 current loops, it is very recommendable to move the dynamics, to make the dynamics of this DC boost voltage regulator a little bit slower, because now there are many sequences, there are many PI controllers, there are many loops working all together. So it is better if we do this dynamic of this, and the dynamics of this DC boost voltage slower. Make it weaker, not so strong. So in order to do that, let's find the initialization program, which is here. Let's go to the parameters of the grid side converter, which are here. These are the parameters of the DC boost voltage, which has been tuned by no criteria, just try and error. Let's do, for instance, the integral term weaker, smaller, 5 times smaller, for instance. Let's initialize, and this is all. Okay, so I think that everything is correct. So let's start the simulation with the accelerator. We will need to wait some time. So it seems it's working now. Let's have a look at what happens. As always, the startup. Here we have the DC boost over voltage, and here we have now the D and Q components and positive and negative sequences. In green we have the negative sequences that for the D case, for the D component is to 0, and for the Q component is also to 0. Here the positive sequence is trying to make this DC boost voltage near to the reference. is about to finish. Okay, so now it will start oscillating, and here we have the oscillations due to the positive and negative sequences of current nodes. There are some oscillations that could be less stronger by doing a more appropriate or more efficient selection of the notch filter that we are using here, but anyways, it is not so important because after some few milliseconds it has been damped, and here we have the decibels. Oh, sorry, the currents of all the elements. This is still oscillating. Now the voltage dip has occurred at second 3. Here we have the asymmetry at the voltage of the grid, and also seen by the grid side converter. At second 3.11 we have the demanding reactive current, what means a positive Q component of reactive current like this, which is positive, and here we have the corresponding currents, the combination of the D and Q component. They are sinusoidal and balanced, they are symmetric due to the zero reference of the negative sequence. Now we have recovered the voltage and the simulation has finished. Everything goes very fast. So let's go again and a little bit slower. Let's summarize what has happened. Again, here we have second 3, the voltage dip. At the rotor side converter we didn't change nothing, so everything should be equivalent as we saw in the 4th tutorial, in 7th tutorial, in previous tutorial. So let's pay attention, or let's focus on what happens after second 3, which is the instant where we have programmed this voltage dip, this asymmetrical voltage dip. Here we are the D and Q components of current behavior, and here we have the voltages, and here we have the sinusoidal ABC currents. Let's do something similar with the rotor side converter magnitudes. We won't go to explain or to comment them because we did in previous tutorial. Basically we can see that nothing has changed compared from the previous one. Very equivalent behavior at this rotor side converter control, but at the grid side converter control, as we said, here we have at second 3 the voltage dip, which is asymmetrical. There is a perturbation at the DC boost voltage, but the current loops for negative and positive at D component, negative and positive for Q components work properly. As we have said before, as we have seen before, there are some oscillation just at the beginning of the voltage dip, and this is due to the oscillations that goes through the notch filter that we have used. We could use a more efficient or a better filter, for instance with a combination of notch filter and low pass filter, or just a low pass filter, or some other type of filtering, but we won't go for those details. This is just a rough introduction to this topic. So here we have the DC boost voltage oscillates, oscillates, and due to the D component positive, these oscillations are damped and we have a proper operation of the grid side converter. Then here at second 3.15 we have the step demand of reactive current, positive reactive current, which is given by the positive current loop. While the negative ones, D and Q, are controlled to 0. With this, what we achieve? What we achieve is currents in ABC which are balanced. We have asymmetry at the voltage, but we have symmetric grid side currents exchange with the grid. And this is due to the negative sequence of currents that we have add to the grid side converter control. Okay, so that was all in this tutorial. I hope it was interesting and useful for you. Thank you for your attention.